In these two examples, we will look at methods for solving rational equations. So the first example is the rational equation 2x over x minus 5 equals 3. This is a great way to start reviewing our steps for solving a rational equation. So first we want to clear the fractions by multiplying both sides of the equation by the lowest common denominator. So after step 1, we should no longer have fractions in our equation. That's the nice thing about rational equations. They might start with fractions, but there's a quick and easy way to eliminate those fractions, so then you result with either just a linear equation or a quadratic equation, which we are more comfortable solving. Or I shouldn't say more comfortable solving, but we're very confident solving those types of equations. So first of all, we want to identify our LCD. So in this first example, the only denominator we have is x minus 5, so the LCD has to be x minus 5. So I'm going to write my original equation, and then I'm going to show that I'm multiplying both sides of my equation by the LCD. Now, on the left, I did multiply it by x minus 5 over 1 because I'm multiplying by the fraction 2x over x minus 5. So it's nice to see both numerators and both denominators. But on the right side, there's no need to put x minus 5 over 1 because all I'm going to do is distribute the 3. Okay, so on the left side of the equation, when I multiply by x minus 5, notice how the numerator x minus 5 will cancel out my denominator x minus 5. So that's really nice. I'm just left with 2x. Now, on the right side, I distribute 3 for the result of 3x minus 15. So now I'm at step 2, where I'm going to solve the resulting equation. Well, my resulting equation is simply a linear equation, so all I have to do is subtract 3x from both sides of the equation. I'm left with negative x equals negative 15. So one more step, divide both sides by negative 1, and x equals positive 15. But now I have to do step 3, where I have to check for extraneous solutions. And we'll look more in depth at extraneous solutions on slide 2. But for right now, just let me tell you that an extraneous solution, it's a solution that you arrive at, but it actually is not part of the domain of the original equation, meaning that it would have made the denominator of the original equation 0, and that is not part of the domain, because we cannot have 0 in the denominator of a rational expression, or we cannot have 0 in the denominator of a fraction. So let's go ahead and check this. So I'm going to just section off my work here to do the check. So I'm going to rewrite my equation, and everywhere that the x value was, I'm going to replace it with 15. So in my numerator, I get 2 times 15, and then in the denominator, it's 15 minus 5. Now, I'm already feeling good because the value x equals 15 does not cause my denominator to equal 0. But let's just keep going and do the check. So I'm going to get 30 over 10, and that's supposed to equal 3. And yes, indeed, it does. 30 over 10 equals 3. So I'm confident that 15 is my solution. Okay, let's look at this next example. I'm going to rewrite the equation, but on the right-hand side, I notice that I need to factor the denominator. So the denominator x squared minus 6x plus 8, that factors to the binomial x minus 4 times the binomial x minus 2. So now that helps me identify my LCD so I can do step 1. The LCD is the product of the two binomials x minus 4, x minus 2. So I'm going to show that I'm going to multiply both sides of my equation by x minus 4 over x minus 2. So on the left-hand side, I'm going to put it over 1 because when I distribute, I will be distributing it to fractions. So it's nice, again, to see the numerator and the denominator. I'm going to do the same thing on the right. So now I'm showing that I'm multiplying both sides by the product x minus 4 times x minus 2. Okay, on the left, when I distribute to the first expression, 1 over x minus 4, the denominator x minus 4 will cancel out. So I'm just left with the remaining numerator x minus 2 times the numerator 1. Now I'm going to distribute again to the second fraction on the left side. And now the denominator x minus 2 will be canceled out by its matching factor x minus 2 from the LCD. So all that remains from the LCD is the factor x minus 4, and I multiply that by the numerator x. Now, on the right side, well, look at what happens. Both factors of the LCD will cancel out. So I'm simply left with the numerator 2. Now I'm going to distribute and combine like terms. While on the left side, if I distribute 1 to the binomial x minus 2, I just have x minus 2. And then I want to distribute x. So now I have x minus 2 plus x squared minus 4x equals 2. Let's combine the like x terms on the left side of the equation. So I'm going to combine 1x minus 4x, and then I'm going to put it in standard form. So x squared minus 3x minus 2 is equal to 2. And so now I'm at the step where I want to solve the resulting equation. This time the equation is quadratic. So I want to set it equal to 0 by subtracting 2 from both sides. So then I have x squared minus 3x minus 4 equals 0. So now I want to factor. I get the binomial x minus 4 times the binomial x plus 1, and that equals 0. And then using my zero product property, I get 2 possible solutions for x. Now, I'm not going to stop and say, okay, I have my solutions, I'm done. No, I'm not going to do that. I need to check for extraneous solutions. So on the next slide, we're going to test both of these, and we're going to see if they cause either of the denominators to equal 0. And if they do, we have to discard that solution. Okay, so let's go on to the next slide. And first of all, let's look at some images of what an extraneous solution actually is. So here's a fancy definition. An extraneous solution is a root of a transformed equation that is not a root of the original equation because it was excluded from the domain of the original equation. So if you think about the domain of a rational expression, basically we cannot include any x values that would cause the denominator to equal 0. Let's look at a little bit of a simpler definition of an extraneous solution. Both good definitions, but this one maybe you just might resonate with a little bit more. This one says extraneous solutions are values we get when solving equations that aren't really solutions to the original equation. And the reason why they're not solutions, though, is because they violate the domain of the original equation. So let's go back and talk about what we mean here. So my original equation, let's recopy it down. It was 1 over x minus 4 plus x over x minus 2. And it was equal to 2 over, now remember we factored the denominator, x minus 4 times x minus 2. And we got 2 possible solutions. And those 2 possible solutions were x equals 4 or x equals -1. Now, you could just plug both of those in everywhere you see x one at a time and check and see if they balance the equation. But at this point, we're just going to check to see if either of those violate the domain. All right, so let's start by checking x equals 4. So what I'm going to do is I'm going to take that value 4, and I'm just going to look at my equation. I'm going to say, okay, if I were to replace the x's with the number 4, is there any instance where a denominator would become 0? Well, yes, there is, right here. And once I see it happen once, I can stop checking. So the rational expression 1 over x minus 4, if I replace the x value with 4, look how I get 1 over 4 minus 4, which is 1 over 0, which is an undefined value. That means the solution x equals 4 violates the domain of that rational expression 1 over x minus 4 because it produces a value of 0 in the denominator. So right away I can eliminate x equals 4. All right, let's check x equals 1. Okay, so now I'm still going to take the value 1, and I'm still going to imagine that I am inputting it everywhere I see the variable x. But now I'm checking to see if any of those denominators turn into 0. Well, If I put negative 1 minus 4, that gives me a denominator of negative 5. That's okay. Negative 1 minus 2, that's a denominator of negative 3. That's okay. And these pieces of the LCD are just repeats. So none of my denominators will become 0 if I substitute in the value x equals negative 1. So I can safely say that my only solution here is the value x equals negative 1. And what that means is the value x equals 4 was what we call an extraneous solution. So I had to get rid of the possible solution x equals 4 because it turns out it violated the domain and it is not a solution. So x equals negative 1 is the only solution.